Hello everyone. Today let's solve the problem number 295. Find find median from data string. Right? You can just go through the question and you can just try to understand the question with the help of example that they have given as well. I'll just summarize the question so that it will be easier to understand. So what the question states here, we need to design a data structure that supports add num here. You can clearly see. So we need to design a data structure that supports add num and find median. So what we will do in the add num, we should be able to insert a number into the data structure. So we should be able to insert a number into the data structure using add num. And what we'll be doing in the find median, so here it returns the median of all inserted numbers so far. So we have to return the median of all inserted numbers so far. Then what is median here mainly? So median is middle value when the numbers are sorted. When the numbers are sorted, then only the median is middle value. So if the count is odd, then the median is the middle element. If the count is even, then the median is average of two middle elements. So here again I'm telling median. What is median? Median is nothing but middle value when the numbers are sorted. If the count is odd, then median is middle element, and if the count is even, then the median is the average of two middle elements. Just keep this one in mind. And one more thing I want to say here is, here the initialization, return value of the initialization and return value of the add num is always void, means null. We are speaking in the JavaScript, right? We are considering JavaScript. So the return value will be null, right? Here for the add num and the initialization. So only for the find median method, the return value is number. Just keep this in mind. So I hope the question is completely clear. So let's dry run this example once we are good with the approach, right? So initially, I have explained the question, so I hope the question is completely clear. So let's discuss the approach and dry run the example that they have given, and then finally write the edge cases one by one, followed by writing the code and discussing the complexity of the code that we have written. Initially, let's go with the approach and dry run the example that they have given in the question. So let's discuss the approach step by step. So we have to find the median after every insertion, right? So let's make use of the two heaps or two priority queues. One is, let's go with the min priority queue and max priority queue. So here, let me go with the max. We are going with the max and min priority queue. Why we are going with max and min priority queue? Because we have to find the median after every insertion, right? So that is the reason we'll be making use of two heaps or two priority queues. So max heap will be considering this one low, will be considering the min priority queue as high. So here this means this stores smaller half, right? This one stores the smaller half. We know that one thing, in the max priority queue, the maximum element will be always on the top, right? So here this stores larger half, larger half. And the minimum priority queue, minimum element will be always on the top, right? So this will be considering low and this will be considering high. So we are going with max and min priority queue, right? So how it works basically. So I'll just give here how it works. Let's see how this works. What will be the approach? First, what we will do, we will insert number, right? So we'll be inserting the number to max heap or max priority queue here. We'll be inserting the number to the max priority queue here. The second step is, we have to move the largest element from low to min heap. So here this stores the small half, but it will contain the largest element at the top, right? So what we have to do here, we have to move the largest element from low to this one min heap, right? Low to high or nothing but min heap. right? This is what we'll be doing in the second step. So what will be the third step then? If low has fewer elements than high, low has fewer elements than high, then what we will do? We will move the smallest. We will be moving the smallest from high to low. From high to low. We'll move the smallest from high to low. So that's what we'll be doing here. Just to balance the correction, this we will be doing. This is necessary part. Even though uh, we can find this one. Even though we find this one quite annoying or tricky, so this is the necessary part. So if low has fewer elements than high, then we have to move the smallest from high back to low, just for the balance correction, right? So next step and the final step, median calculation. So we have to calculate the median, right? So this is median calculation. So how can we calculate the median? So we have already discussed this one, right? So I said one thing during the question: if the count is odd, then the median is the middle element. If the count is even, then the median is the average of two middle elements, right? If low has if low has more elements, then we will be considering low dot front. As we are dealing with the priority queue, we can go with the queue property, right? Front. If low and high are equal, if low has more elements, then we are considering low dot front. So if low and high are equal, then what we will do? In that case, we'll be considering low dot front, same thing, plus high dot front here. In this case, just give me a second here. High dot front, this one by 2. So this we know. During the question itself, I have said the same thing. If the count is odd, the median is the middle element. If the count is even, the median is the average of two middle elements, right? That is the reason. So this is what the median. This is how to calculate the median basically. So what is the approach? Basically, we are going with max and min heap, and max heap stores the small half. Nothing but largest value will be on top always. Min heap stores the larger half. Smallest value will be on top always. So how it works basically? First, we will insert the number into the max heap. Second, what we'll do? We'll move the largest element from low to min heap. Nothing but high. Third thing is, this is important. If low has fewer elements than high, then we are moving the smallest from high back to low, just for the balancing. So fourth one is median calculation. So if low has more elements, then low dot front will give. If low and high are equal, then we are going with low dot front plus high dot front by 2. This is what we'll be doing. So what will be the time complexity here? So for insertion, it takes big O of log n, right? For the insertion, it takes big O of logarithmic n, and for the median retrieval, it takes big O of 1, right? This is for insertion, and this is for median retrieval, right? I hope this is clear. Big O of log n for the insertion and big O of 1 for the median retrieval, right? So let's dry run the code accordingly with the approach. Let's dry run the example that they have given in the question, right? So accordingly with the approach that we have discussed now. So this is the example that they have given in the question, right? The same thing will be considering. Let's see the step-by-step execution. The first thing we have to consider here is median finder and this one, right? Empty array. So here, let's initialize the median finder. So first step, nothing but initialization. So I'll just give you initialization or initialize. So this will be initialization. Low, nothing but max heap we are considering, right? Max and min heap. This will be empty array. So min heap we have considered high. this one is also empty array initially. So output will be null for this. We know that it doesn't return anything, right? Initialization step. So only this one, find median, returns the number. So all other things, all other methods return basically null, including the initialization part. Let's come to the step 2 here. We are adding 1 in this case. You can clearly see add num of 1, right? So we are adding 1 here. So add of 1. Let's insert 1 to low here. Nothing but low. Now this will be equal to 1, right? So high remains empty. So high still remains empty itself. This will remain empty. Low will be 1. We are just inserting. This is add of 1 operation we are doing. So we are inserting 1 to low. Low will be 1 and high will be empty. So no balancing is required. So still the output will be null because the method add returns void or null as per the return they have given in the code, right? So the return value is still null. Let's go with the third step here. Let's go with the third step here. What we need to consider here. Third step, add num of 2. Now what we do? Now we have to add 2 here in this case. So we are adding 2 here in this case. Now insert 2 to insert 2 into low, right? So we are just inserting this one to the low. Now low becomes 2, 1. So we already have 1. We are just inserting. This will be 2, 1 because see here we have inserted 1 previously. We already have 1 in low. So now it will be 2, 1, right? Max heap keeps the largest on top. So this we are considering 2 will be first and 1 will be next, right? So we are moving the largest from low to high. Now low will be 1 and high will be 2 because max heap keeps largest on the top. So now heaps are balanced. Output is still null because the return value of the add is null. We are going with the add method right here. So let's move on with the step 4. Let's consider the step 4 here. Step 4, what they have given. Let's see first what they have given, man. So this one, find median of empty braces they have given here. We don't have any element here, right? So this will be find median. Empty array they have given. So here, as we have discussed in the this one approach, it is low.size. If size is equal to high, size of the high, then median will be low.top plus high.top divided by 2. In this case, low is 1. We know that where I have written here. Yeah, low 1 and high is 2. From the previous step, we know this one. Nothing but 1 plus 2 here by 2, right? 1 plus 2 by 2 is nothing but 3 by 2 here. In this case, output is 1.5. So the output is 1.5 here. Find median for the find median method. So next, let's go with the next one. Let's move on to the next one. Here, add num of 3 we have to consider right here. Add num of 3. So I'll just consider here. This is step 5, right? Add num of 3. This case, we have to insert 3 into low. We are inserting 3 into low. So I'll just give here insert 3 into low. So now low will be 3, 1, right? So we have to move the largest from low to high. So now low will be 1 and high will be 2, 3, right? So we are just moving the largest 3 from low to high. Now low will be 1 and high will be 2, 3. Again, so we know this one from the approach. When size of the low this one is less than size of the high, then we will move 2 back from high to low. Then now low will be 2, 1 and high will be 3 in this case, right? I hope this one is clear. So still the output is null itself. Why the output is null? Again, the return value of add is null, right? So let's move on to the next one or the last one. So I'll just come here. Let me consider this one. Find median of empty array. So let me consider this one. So we have to find median, right? So empty array they have given. So now we know that, just give me a second here, find median. We know that one thing here, size of the low is greater than the size of the high, right? So size of the low is greater than the size of the high. So median will be low dot top, right? So here median, sorry, just give me a second here. Median in this case will be low dot top. We know that here at the top it is 2 here, right? You can clearly see here low dot top, nothing but the first element is 2 here in this case. So 2 will be the output. From the previous one we know that low dot top is nothing but 2. So 2 will be the output. Output will be here 2 or 2.0 we can consider, right? So the final output that we got here is, just give me a second here. From here we started, right? Null, 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 3 times null, and fourth one is 1.5. 1.5 again null, 3 times null, 1.5 null, and finally 2.0. So here let me go to the next page. Output here is null, 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 1.5, null, and finally 2.0. This is what they have showed in the example as well as output. So the approach works absolutely fine if you are making use of min and max priority queue for this problem. So let's quickly discuss the edge cases one by one and then finally write the code. Here let's discuss the edge cases one by one. So I'll just give you edge cases. So the first edge case that we are going with here is single element. I'll just give here single element. This is for the condition single element. So the input, let me consider 1 here. So the median will be obviously, or the output will be 1 because we have only one element. So this is for the first edge case. Second edge case is for even number of elements. This is for the condition even number of elements here. This is fine. So let's consider here even number. So I'll just consider 1 and 2 as input. For the even number, we'll just go with this one, right? 1 plus 2 by 2 here. This will be 1.5. 3 by 2 is nothing but 1.5. Here output will be 1.5 for this one. This is for the condition even number of elements. Let's move on with the third edge case. Third edge case we are going with odd number of elements. Odd number of elements, right? So this one, let's consider odd number of elements. Let me consider odd number of elements within the array, right? So this one, 1, 2, 3. Here median will be obviously 2. For the odd, middle value will be considered as the median, right? So here the median will be quite obviously 2 in this case. So for the fourth one, let's consider all elements same here. So I'll just give here, this is for the condition all elements are same. So when I say all elements are same, let me consider input 5, 5. Any number you can consider just for the simplicity and to understand quickly, I'll just take 5 4 times. So median will be 5 here. So we can just go for here middle two values, right? 5 plus 5 by 2. This will be 10 by 2, nothing but 5. 5 will be the answer. So let's go with the fifth edge case, nothing but negative numbers. So when I say negative numbers, let's consider the input here -3, -1, -2. So median will be again -2 in this case. Why the median will be -2? Here we have three numbers. We can just add all the numbers here, right? So here this will be -6 by the number of elements we have is 3. This will be -2 here. The output will be -2. Let's move on with the final edge case, nothing but large range. So when I say large range, we will be considering accordingly with the constraint. I'll just go with here input -10 to the power of 5 to the positive 10 to the power of 5, -10 to the power of 5 to the 10 to the power of 5. This has to handle large values efficiently. Anything, output may be anything, but I've just considered this has to be within -10 to the power of 5 to 10 to the power of 5 to positive 10 to the power of 5 efficiently, right? This is fine. So what are the edge cases that we need to keep in mind here? This one is for the single element. Yeah, this one is for the even number of elements. This is for this one odd number of elements. In this case, we are just going with replace 6 by 3 here, right? So let me show the calculation as well. 6 by 3 here, nothing but 2. So here also we can just go with this one, or we can just go with 5 this one 20. We can just add up all the things, and by 4 this will be 5, right? So this is also fine. So fifth one is for the negative numbers. We saw for the negative numbers, and final one is for the large range. I hope all the edge cases are clear. Now let's start writing the code. I'll explain the code while writing the code itself, right? And then finally discuss the complexities of the code that we have written. So whenever we are asked to design something, it's better to go with the low level code. So I'll just be making use of the class instead of the function here. So one more thing we have to keep in mind. So for the initialization, we'll be making use of the constructor within the class, and these two methods will remain same. Within the class, we'll be making use of add num and the find median methods as functions, right? So this is fine. And one more thing, return value of this one initialization as well as the add num remains void or null, and the return value of the find median will be number. Just keep this one in mind. So let's start writing the code here. So this will be median finder, right? This is fine. Let's go with the initialization. This will be constructor. So within the constructor, what we'll define? So we are going with the max heap and min heap as per the approach that we have discussed, right? So max heap, nothing but lower half to store the smaller numbers. So let me initialize this one. This dot high. We have considered this one. We have seen this one already, or we have discussed this one already within the approach, and we saw how to implement this one by considering the example, right? So writing code must be easier now. So minimum priority, right? Minimum priority queue. This is fine. I'll just copy the same thing here. We're making use of max heap and min heap. For the min heap, let me consider here this one low instead of high, and let me consider this one min, right? So maximum heap to store the smaller numbers, and min heap to store the larger numbers. This is it for the initialization or the constructor. So let's come out of this one. We had two this one methods, if you remember. One is add number and another one is find median. Let's go with the add number. We have n here. Let me pass n here within this one as parameter. So what was the first step that we discussed? We have to add the number, right? We have to insert the number to the max heap, if you remember. So this one will be dot low, right? For the max heap we have considered low dot. For the insertion queue property, we have nq. Within the nq, let's give n here. This is fine. So the next step is we have to move the largest from the max heap to the min heap. Nothing but from low to high. We have to move the largest from low to high or max heap to min heap. So how can I articulate this one in the form of code? I can just write here start high dot enq of just give me a second. Yeah, this dot low dq dot element. This is fine. And the next step is we have to balance the heaps if necessary. So how can we write that? Start low size, this one, this dot, if it is less than size of the high, then we can write this in this way. This we had discussed. If low has fewer this one, right, than high, then we have to balance. That's what we had discussed in approach, if you remember. So how can we articulate in this one in the form of code? I can just give here this dot low dot enq, this one, this dot high dq element. This is fine. So this is it for the insertion or adding the number, right? So next, the final step is find median. So we are just going with the find median function or find median method here. This is fine. So if you remember, within the find median, to find the median, what we have discussed, if the max heap has more elements, then we have to return the top element. Otherwise, we have to return the average of both the tops, right? So this one has to be low dot size. The size of the low, max heap has more elements, then we have to return the top element. Means size of the low is greater than the size of the high we are considering here. This dot size, sorry, this dot high we have to give here a size. So then we have to return the top element. So for returning the top element, we have the property front in queue. Front and rear we have, right? We can just make use of the front in this case. So I'll just give here this dot low dot front element. This is fine. I hope this is clear. So otherwise, if max heap has more elements, we are returning the top element. If max heap has less elements, then what we will do? We will return the average of both tops. So I can just write it in this way. Return low front. This is 5. Same thing, I should have copy pasted this one. This is 5. Element. We have to return the average of both the tops, right? How can we write this one, or how can we articulate this one? So this one I'll just give here this dot high dot front. So just give me a second here. Front dot element. This is fine. Element overall by 2, right? I hope this is clear. We are just if the max heap has more elements, we are just returning the top element in this case. If otherwise, we are returning the average of both this one. Average of both tops. That's what we are doing here. I hope this is clear. That's what we did here, right? So I hope this is clear. First, we went with the initialization. Next, we went with addNum function. Next, we went with the find median function or method. So I hope this is completely clear. So this is it. Let me, yeah, this is fine. Let me format the code once and let me hit the run button. So you can clearly see the sample test case is getting passed here. So the code works absolutely fine. Let me hit the submit button then. So you can clearly see here all the test cases are getting passed here. So the code works absolutely correct. So what is the approach that we went with here? This is completely priority queue based or heap based. We can just say it's a mixture of min heap and max heap. I mean min priority queue and the max priority queue. So what will be the time complexity here? The time complexity we have already discussed here. For the insertion, it is big O of log n, right? So we know this. We have already discussed this one. This one will be big O of log n, and for this one, for the insertion, it is big O of log n, and for finding median or find median method, so sorry, it is big O of 1. For the insertion or adding the number or add num, for this one, it is big O of logarithmic n, and for find median, the time complexity is big O of 1. I hope this is clear. Then what would be the space complexity here? The space complexity for both, it will be big O of n. Why it is big O of n? Because to store the elements in the heaps, it takes big O of n space complexity, right? It takes big O of n space. So heap or priority queue, it can store up to n elements at worst case. So the space complexity will be big O of n here. So now we know the time complexity for the insertion is big O of logarithmic n, and for the find median it is big O of 1, and the space complexity for both is big O of n. I hope this is completely clear, right? I hope the solution is also completely clear. For now, this is it. Thanks for watching, guys.